The festival of Onam has just concluded here in Kerala. Onam is a wonderful festival. It unites all the people together, irrespective of religion. And there's a lot of fun and frolic and a lot of things to eat and a lot of events and a lot of decorations. One of the decorations you may have seen on the internet about this particular festival would be this decoration made out of flowers. Usually they are circle in shape, but need not be always. And they're made out of petals of flowers arranged in a beautiful manner. But Kerala does have another way of arranging a design in front of the threshold of a house, the main entrance door. A lot of Hindus, what they do is they create what is known as a kolam. I may be pronouncing it incorrectly. And it's very fascinating. There are some very nice designs which you can see over there. If you were to look at these designs, there are certain patterns which are little difficult to understand because it's so captivating. It's very intriguing. And these kind of designs broadly come in the category of fractals. Now, what are these fractals? And let us delve into this because this has got something to do with what I spoke earlier about complexity in architecture, where I explained how one can go from very simple set of spaces to a very complex spaces, and we need to determine which is the kind of complexity or simplicity which we need to achieve. One of the misunderstandings of that particular talk maybe is that if you have to do something very simple, it also becomes very boring, because I happen to give a very boring example in architecture to describe something simple. But simplicity need not be boring at all. And that is why I chose this particular subject on fractals in architecture. Because fractal is actually a very, very simple thing. It is so simple that you can actually describe it in a few rules. And because you can describe it as a small set of rules, you can compress it very, very small, those rules that is. And therefore, it does have a very low K complexity, Kolmogorov complexity. Now, what are these fractals? One of the unfortunate things about the human mind is that we give a lot of importance to what we see in front of us. Our vision is often very deceptive. And nowadays, fractals are being taught in architecture schools, and unfortunately, they are being taught quite a lot of times in the same bad way as the way geometry is being taught, and if it is ever properly taught at all. Now, what are fractals? So, fractals has to be understood from the point of view of the way it the eventual visual appearance come about. So instead of getting fixated on the visual appearance, we must understand the underlying informational process going on in the back of it, which is sometimes it is a little tough to explain to people who are fixated on the visual aspects. So let me first differentiate between what is complex and what is intricate. These are very similar words. Like when you see something extremely intricate, like this column decorations and various types of fractals, you get so captivated by the intricacy of it, you may assume that it is very complex, but it is actually not at all complex. So in management, they use another kind of confusing term. They say something can be complex or complicated. Well, I don't want to get into that. What I meant by complex is, in common parlance, what is complex, which is very difficult to comprehend and understand. Those are complex. Intricate things can seem to be complex, but they are not. Some of them are not, at least. Some of them could be a little complex, but many intricate things are not complex. They are just uh, intricate. anyway, anyway, I think you get the point. So, so what I'm trying to tell you here is to give you the confidence that just because we have this whole Kolmogorov scale of complexity, that we necessarily have to go towards the complex end to make something very breathtaking and intricate. No, not really. You can do that using fractals, and for time immemorial almost, we in India and some places in Africa, we have innately understood this concept of a fractal. So let me explain it in a slightly roundabout way. Think of a household where this column has to be, decoration has to be made, and there's a lot of excitement in the house, and because these festivities going to come soon, and there is a lot of laughter and joy and everything, and that lady has to now make that column outside that entrance. Now, if that lady has to really think through and identify each and every part of that piece of work which she's about to do, and start thinking that, oh, should I put this here, and then say, okay, let me think about it, put that there. There's not enough time for that, because there's a lot of work going on, and there's food to be prepared, paisam to be made, and all kinds of things going on. So what society in here in Kerala and other places ended up doing is that it gravitated towards a simple set of rules which gets repeated at multiple scales. So that lady takes that powder. The columns are made from powder, and pookalams are made using flower petals. So these columns are traditionally made out of white powder, maybe rice powder. You can look that up. I may be wrong about it, and it's arranged in such a way the eventual result is very intricate, but actually the thing which is guiding that lady is a very simple set of rules which she kind of automatically forms in her mind, and then she does it at various different scales, and out there you get the eventual column, which is pretty intricate and pretty fascinating to look at. Some people may even think that it is very complex to create. In fact, there are a lot of such decorations in India. In Maharashtra, they use this mehendi before. In Maharashtra and many places in North India, before marriage, they decorate their hands with henna, and you have very intricate designs. And there also, really speaking, there's a simple set of rules which are repeated in some nice curvy manner, and all kinds of things happen, and you get a beautiful intricate design on that person's hands. So fractals, to understand fractals, fractal is a part of geometry. You can say it's a kind of a curve. uh, I don't know whether you should call it a curve, but the visual appearance of a fractals comes because of its underlying rules, which are self-repeating rules at different scales. Now, the fascinating thing about fractals is that nature kind of caught on to this. And if you see a lot of natural forms, the way branching of uh, uh, trees and plants, the way it branches out, the nature of the branching, or the arrangement of the leaves, or the leaflets on a leaf, these are all based on internal fractal rules, for pretty much the same reason as that excited lady who's quite occupied with many other things. She has to make that decoration, so the rules have to be very simple, and eventually you get something very intricate. It's the same reason why a plant ends up with these fractal rules are working in the backdrop, which is embedded into its DNA and its genome, and that genomic rules guide how it should branch itself, and then it results in this beautiful greenery which we see around us. Why greenery? In fact, if you look at it, there are even non-biological things like chemical reactions which can take up a fractal nature for again for similar reasons of minimal set of rules which are iteratively repeated at different scales, and it produces the end results. To understand this, it's very important to stress the underlying construction of this system. You must understand that, and unless and until the underlying processes are known, we may end up kind of glorifying something like fractals. So I call it the second mistake in geometry, because the first mistake in geometry was also the same, where we taught students only the outward visual appearances without telling them these are all appearing as traces of certain processes happening in the backdrop. For example, if I pin a thread and then hold a pencil and then I rotate around that center point which is pinned, I get a circle. Along the same lines, you can actually put two pins and take a thread and put a pencil, and then you can trace an ellipse. So it is actually because of the activity of that string and that pencil that you got a circle or an ellipse or whatever the case may be. And it's the same case with almost all of geometry. So unfortunately, geometry is taught from the visual point of view in many cases, and that is extremely misleading, and it makes the whole subject very boring. But if you were to really understand how this has to be how these processes work, you can really get a lot of insight about how geometry works. Uh, Let me take a small digression and explain a very interesting thing which had happened. I was that time an associate for Hafiz Contractor, and one clubhouse was kind of already under construction when I joined, and a colonnade had already been created. Now, Hafiz wanted a set of arches over there, semicircular arches, but for some strange reason, the columns on which these arches have to be made for that colonnade, they were not of the same intervals. So it was, say, one was, say, 10 feet, the other one was 11 feet 3 inch, the third one was 12 feet, the other one was for 9 feet 9 inch, and so it was a little haphazard. So when I started wondering that now we have to create these arches on top of it. Now the contractors thought that all they have to do is to make semicircles. I said that wait. If you make semicircles on top of it, semicircular arches on top of it, and if you were to look at the colonnade from the side, it will be glaringly obvious. It'll go up and down the apex of it, and it'll be very noticeable. Just by itself, it was not very noticeable. The just by the columns themselves, it was not noticeable because the arches had not yet come up. So then I said that, okay, let me not use semicircles everywhere. Instead, let me create one semicircle for something which I thought would be a reasonable average of this. There were quite a lot of intervals, quite a lot of columns. And then for the rest of it, what I did is that I fixed the top portion of that arch the same everywhere. So obviously the other arches cannot be semicircular. Now I could go for a segmented arch, okay, which doesn't spring at a 90 degrees. A semicircle will spring at 90 degrees, right? But a segmented arch will come with a different angle, and that also would be noticeable. So I settled for ellipses there. And then I showed the contractor how you can make different ellipses, and they were rather thrilled with the whole thing because it was the first time they were working with ellipses, and I showed them how it can be made, how it can be constructed. So they constructed that, and I bet if you go to that club, you will never realize that they are actually not uniform base in the colonnade, because it looks pretty uniform. All the tops are matching, and they all spring at 90 degrees, and it looks pretty nice. So why am I mentioning this is because you can actually have a lot of intricacies in your design, and still maintain a low Kolmogorov complexity number for what you're doing. And if you were to really understand fractals, you'll find that there are remarkably few rules which go into constructing these fractals. In ancient India, when you look at all the temples and the way the temples, they have this pyramidical structure on top in many places in India, you'll find actually it is a fractal structure, because again it's the same kind of wanting to go for reasonably understandable rules which can be repeated at different scales of construction. And then you got these beautiful looking temples, and very very intricate. It looks very complex, but they are not complex. They are a resultant of the set of rules which are applied at different scales. So, just like the way we had calculated the Kolmogorov complexity earlier in my earlier talk, here also, if you were to calculate the Kolmogorov complexity, you will find that fractals compress very nicely. There is a wonderful book you must read. It is called The Algorithmic Beauty of Plants. It is by two people. One person's name, unfortunately, I can't pronounce. I'll write down here later on when I edit this video. And the other person is Lyndon Mayer. Lyndon Mayer and this the other person together, they worked out a whole lot of kind of a language, a rule language, and you can actually describe pretty intricate natural forms like trees and shrubs and ferns and leaves and everything using what is now called as L systems. It's very fascinating. So you can actually just write a few rules. Literally, it won't even cover half a page, and you can actually, it results in a beautiful fractal and beautiful botanical forms mainly. So that's why the book is called Algorithmic Beauty of Plants. And the obviously the Kolmogorov complexity will be very small for these kind of construction. Now, before I end, I must also tell you that fractals need not be actually something that's readily apparent in front of you. A lot of fractals are actually hidden. Like there's a fractal in our lungs, there are fractals in our brain, there are fractals in our nervous system. They're all not visible. But along with that, there are actually fractals which can be made by arranging space itself, and you may not be able to perceive that visually directly, but internally it is a fractal, and that's a subtopic for later, where I'll explain how spaces itself can be arranged as fractals. So I hope this is got clarified. The point being clarified is that you can have something which has got pretty low complexity, but still be extremely, what do you say, intricate. And all these experiments and trying out various types of code can be done in TAD in my software. I hope you'll take a look at it, and I hope to see you in my next video. Thank you very much.